Good day. I'm Lloyd Dixon. Today we're going to do a tutorial on magnetic design for switching power supplies. This tutorial is in 5 sections. They were presented originally at Unitrode Switching Power Supply Design Seminars in 1997 through 2000. Before you get into this tutorial, I would urge you strongly to obtain a copy of the Unitrode Magnetic Design Handbook, which not only covers much more detail on the 5 topics that we will be discussing today, but also contains additional reference material from previous Unitrode seminars on magnetic design, which altogether makes a textbook for this course. Section 1 deals with basic magnetic theory. Those of you who have been involved in switch mode power supply design will certainly recognize the fact that success or failure is often dictated by the design of the magnetic components. You may depend upon some individual or organization to do your magnetic design, but this magnetic designer is not likely to understand fully the circuit implications of what he is doing. You need to have enough basic practical magnetic knowledge to be able to carry on an intelligent dialogue with your designer. Unfortunately, our technical schools have done a very poor job, with few exceptions, in teaching practical magnetics design. They cover Maxwell's equations pretty thoroughly, but beyond that, you're kind of left to your own devices. Figure 1-1 shows the electrical equivalent circuit of what might be a forward converter power transformer, but this equivalent circuit shows all of the parasitics that are associated with that device. Normally we don't see those parasitics in the circuit diagram, but with a proper model of the circuit, including the parasitics, running this in a SPICE program, the effect of these parasitics on circuit performance can be determined. For example, look at the inductance labeled L1-2. This represents the leakage inductance between the 2 secondaries, and as shown, it is located in series with secondary number 2. It can make a great deal of difference whether that leakage inductance is located where it is, or in series with S1, or shared between the 2 outputs. There is a topic in the reference section of the Magnetic Design Handbook entitled Deriving the Equivalent Electrical Circuit from the Magnetic Device Physical Properties. This topic will show you not only how to develop the equivalent circuit with the proper location of the parasitic elements based on the device structure, but can also crudely quantify the values of these parasitic elements. Armed with this knowledge, you can go to your magnetic designer and say, Charlie, why don't you change the sequence of those 2 secondaries, and this will put the leakage inductance in a more favorable location. So, if you invest a little time in developing your skill with magnetic design, at a minimum, you should be able to collaborate more effectively with your magnetic designer, or hopefully you may be able to do most of the magnetic design yourself. Where the expertise of the magnetic professional really is important is in issues of manufacturing, manufacturability, reliability, and so forth. But the theoretical aspects are something that you should be able to deal with yourself. The magnetics theory required for the successful design of switching power supply components is really not all that difficult. But unfortunately, most of us are inhibited when it comes to this subject. This stems partly from the engineering education that we have received, which, with rare exception, has been quite poor in practical magnetics. Most of the design concepts and resulting equations that are in use today for practical magnetic design were developed over a century ago by our great-grandparents. I'm convinced that they knew more about practical magnetics than we do today. However, they had one big problem that we don't have today, and that is the difficulty of making computations. Magnetic design is rather intensive in terms of calculation. Without computers, our ancestors developed concepts that minimize the need for calculation. This usually resulted in design equations that were littered with constants, which made these equations difficult to understand. And not only that, but they perhaps included factors such as peak to average conversion of a sine wave, which are totally inappropriate for the rectangular waveforms involved with switching power supplies. In addition, in the United States, we are burdened with the fact that in the magnetics realm, the CGS system of units is still the most popular. In the unrationalized CGS system, the basic equations include constants that make the equations less intelligible. On the other hand, in the SI system, which is rationalized MKS, the equations become very simple and free of these bewildering constants. Now, if you are well versed in the CGS system applied to magnetic design, I'm not going to try to convince you to change. But if you're just learning magnetic design, I would strongly urge you to use the SI system. Another difficulty that many of us have is that with magnetics we are dealing primarily with energy and time, and many of us are much less comfortable with this than dealing with power in the electrical realm. In the past, I would get involved in magnetic design perhaps only once or twice a year. On each new re-involvement, I would have to go back and learn the approach that I should take. I would go to my limited library, which consisted largely of manufacturers' data sheets and design approaches offered by these manufacturers. Every one of them seemed to take a somewhat different approach. It would take me maybe a day or two to get everything sorted out and get my feet back on the ground. I really began to make progress in magnetic design in terms of a true understanding only when I decided to throw out all this information, much of which had these incorrect, archaic concepts, and go back to the very basics and use the SI system. And when I did this, then the light dawned and things became much more simple. This illustration shows the magnetic field surrounding a pair of conductors in close proximity to each other. This pair of wires is carrying current into the screen. Let's imagine there's a load at some distant point and a source that's behind us. Let's imagine that we have 6 amperes flowing in the right-hand conductor, flowing into the screen and returning out of the left-hand conductor. The field created by these current flows will result in the pattern that you're observing. The magnetic field has 2 components, magnetic force and magnetic flux. Flux is indicated by the solid lines. The magnetic force is indicated by a series of equipotential surfaces shown as dashed lines. The lines indicating the equipotential surfaces are actually the edge view of these surfaces. Field intensity is indicated by how close these surfaces are to each other, and flux density is indicated by the proximity of the solid lines showing the flux. You will notice that close to the conductors and in the region between the 2 conductors, the field intensity and the flux density are both relatively high. Whereas, as we move away from the 2 conductors, the field intensity and flux density drop off rather rapidly. If the 2 conductors were far apart, the magnetic field surrounding one conductor would be so weak by the time it reached the other conductor that it would have no effect, and then we would see a perfectly symmetrical radial magnetic field surrounding each conductor. But when the 2 conductors are brought close together, as shown, the fields interact to result in a stronger field between the 2 conductors, and the field components subtract as we move away from the 2 conductors and tend to cancel. From a circuit point of view, we think of this pair of wires as having a certain inductance, which represents its ability to store energy. The energy is actually stored in the magnetic field. The energy density at any point within the field is calculated as the product of the flux density times the field intensity, 1/2 BH. It turns out that most of the energy stored in the magnetic field is in the region between the two conductors, the region of high energy density. Although the magnetic field extends to infinity, the energy density drops off much more rapidly, moving away from the conductor pair, than the volume increases. There are 6 or 7 simple basic rules that govern the magnetic field and the way that it arranges itself around these conductors. The most important basic rule is the law of conservation of energy. This dictates that the field pattern will set itself up in a manner to minimize the stored energy. If our purpose is to minimize inductance, this is equivalent to saying we want to minimize the stored energy, and this can be accomplished if we understand the rules of behavior and structure the situation so that the law of conservation of energy can produce the desired result. Figure 1-3 shows the magnetic field associated with an air core winding of 8 turns. Around each wire individually, the magnetic field would be perfectly symmetrical and radial. But when the wires are put together in this coil, reinforcement takes place through the center of the coil as these radial symmetrical magnetic fields add vectorially. On the other hand, external to the coil, cancellation takes place. So within the field, within the coil, we have a concentrated field that is quite linear as shown. External to the coil, the field intensity drops off rapidly. However, in this unshielded situation, this can result in considerable noise and EMI propagated to the outside world. If it is desired to eliminate the coupling to the external environment, this can be done only by shunting the field, by putting the coil in a box, if you will, of magnetic material with high permeability. This magnetic short circuit will cause the flux lines to pass through the magnetic material and decouple them from the external environment. Unlike the electrical realm, there is no such thing as magnetic insulation. This would require a permeability of 0, and a permeability of 0 does not exist. Some of the important principles that govern the magnetic field are as follows. The magnetic force is directly proportional to the current in the winding, according to Amperes' law, which will be discussed very shortly. The magnetic field is made up of a series of equipotential surfaces indicated by the dashed lines. The equipotential surfaces are not infinite. They are bounded and terminated by the current flow that is producing the field. On the other hand, flux is in the form of lines, which are all closed loops. They close upon themselves. No flux line ever originates or terminates. Within any volume anywhere in the universe, the number of flux lines entering that volume must equal the number of flux lines leaving that volume, because no flux line can ever originate or ever terminate. The flux lines are always normal to the equipotential surfaces within a given material, and the flux density is proportional to the field intensity. The constant of proportionality is what is called permeability, mu. Therefore, flux density, B, equals permeability, mu, times field intensity. And finally, the most important rule of behavior is the law of conservation of energy, which guarantees that the field will assume a form that will minimize the stored energy, and this principle can often be used to our advantage. Figure 1-4 shows the BH characteristic of what might be a power ferrite material. The BH characteristic, or hysteresis loop, is often used by the manufacturer to describe the characteristic of a magnetic material. This characteristic would theoretically apply to any core made of this material. The slope of any line on this set of axes, B and H, is the permeability mu of the material. If we decide to use this material in designing a magnetic device, and if we then select, at least tentatively, a specific core made of this material, we can go to the manufacturer's data sheet and find the specific cross-section area of this core and the magnetic path length. If we multiply the flux density axis of this drawing by the magnetic cross-section area of the specific core we are planning to use, the flux density axis becomes transformed to total flux. This assumes that the flux density is uniformly distributed in the cross-sectional magnetic area of this core. This assumption is good enough to result in acceptable accuracy. If the field intensity axis, H, is multiplied by the magnetic path length of the specific core, then the field intensity axis becomes transformed into total magnetic force. So now we have a new set of axes, flux and force. These describe the hysteresis loop, rather, in terms of the specific core made of this material. The slope plotted on this new set of axes, phi over f, is what is called permeance. Finally, if we decide to wind a winding of n turns on this core, the subsequent transformation takes place. If we multiply the flux axis by the number of turns, the vertical axis becomes transformed to integral volt-seconds. This is in accordance to Faraday's law, which relates the magnetic properties, the flux specifically, to volt-seconds applied to the winding. If we divide the magnetic force by the number of turns in the winding, the horizontal axis is transformed now into current, according to Ampere's law. So the new set of axes now, integral volt-seconds on the vertical and current on the horizontal, is purely in electrical terms. The slope of a line plotted on this new set of axes is inductance. Throughout this process of transformation, the surface represented by these two axes is always energy. B and H represents the energy per unit volume in the magnetic material. Flux phi versus F represents the energy stored in the entire core made of this material. And finally, integral volt-seconds and current define energy of this entire device expressed in the electrical parameters as seen across the coil. Now, to change energy requires time. Energy cannot be changed instantaneously. Power can, but not energy. So to move about on this surface defined by the pair of axes requires time. Cannot happen instantaneously. Specifically, it takes time to move on the vertical axis. It takes no time, theoretically, to move on the horizontal axis. Thinking of B and H, it's hard to imagine why it takes time to move vertically but not horizontally. But if we look at the electrical equivalent parameters, we see clearly the vertical axis involves time, integral volt-seconds, whereas the horizontal axis, just current, does not involve time directly. Now, we think of an inductor as a device where it is impossible to change the current instantaneously. And that seems to be in contradiction to what we are just saying here, that the movement on the horizontal axis is not constrained by time. But it is constrained only indirectly, because if we have an inductor made of this core material, we are constrained to follow that characteristic. And we are also constrained on the vertical axis by time, as shown, integral volt-seconds. This means that indirectly we are also constrained on the horizontal axis as well. But if we imagine a characteristic which is horizontal, we can traverse that characteristic instantaneously because no vertical motion would be involved. Finally, if you are intimidated by the magnetic characteristics, if you find it difficult to think in terms of flux density and field intensity, then think in terms of just the electrical equivalent. Think of a strange device here that is an electrical device plotted on this set of axes. Integral volt-seconds is on the vertical axis and current is on the horizontal axis. Forget that magnetics even exists. This is just an electrical device with this characteristic defined in electrical terms. That may help you to get over one of your hang-ups in dealing with magnetics. Just imagine that it's a pure electrical device. Now you'll have enough trouble dealing with the fact that time is involved here. This vertical axis is not voltage. This table shows the important magnetic parameters expressed in the SI system of units and in the CGS system, and the conversion factors from CGS to SI. Notice that the important difference between these two systems is that in the CGS system, the absolute permeability of free space or any non-magnetic material is taken to be 1. Whereas in the SI system, the absolute permeability of free space is 4 pi times 10 to the minus 7. Now this might seem that the CGS system is therefore simpler than the SI system, but the opposite is true. In the CGS system, this constant, 4 pi times 10 to the minus 7, a rationalization constant, doesn't just disappear. Instead, it appears as fragments in all of the CGS equations, rendering them much less intuitive. In the SI system, on the other hand, the equations are clean and simple and neat and much easier to understand and to remember. Ampere's law shows the relationship between magnetic force and current. In fact, in the SI system, the units of magnetic force is in amperes, or ampere turns to the engineer. The magnetic force along any closed path of integration, integral HDL, is equal to the amperes enclosed by that path. Suppose we have 10 amperes flowing into the screen at the point indicated by the number 1 enclosed in parentheses. It doesn't matter whether we had one wire carrying 10 amperes or 10 turns of wire each carrying 1 ampere. A 10 ampere field is created around that wire along any closed loop path. Suppose we take a path of integration like so. It doesn't matter how crazy that path is or what its shape is, any path forming a closed loop that closes upon itself will have a total magnetic force along that path equal to 10 amperes. Now, if that path were a perfect circle centered on the current flow, I could easily calculate the field intensity along that path. The field intensity would be constant. It would equal 10 amperes divided by the circumference of that circle. But if the path were irregular and not centered on that current flow, then I would be hard put to calculate the field intensity along that path. But I know clearly that the total force around that path is equal to the enclosed current. Notice that in the CGS system, the magnetic force is not expressed in amperes, but in Gilberts. Even though the force is indeed proportional to current, the equality is spoiled by the factor 0.4 pi. This is a portion of that rationalization term, and it means that the current cannot be expressed directly in amperes. Faraday's law defines the relationship between magnetic flux and voltage. Specifically, the rate of change of flux through a coil of wire is equal to the volts per turn applied to that winding. Not the flux, but the rate of change of flux. If we integrate that relationship, then the total change in flux is equal to 1 over n times the integral volts-seconds applied to the winding. This demonstrates, as we said earlier, that flux cannot change instantaneously. It takes time, takes volts-seconds specifically. Notice in the CGS equivalent expression, the factor 10 to the 8th appears. This is part of the rationalization constant that is eliminated from the SI equations. The energy density is the integral h dB integrating along the vertical axis. In the case where the characteristic were a straight line, this integral h dB simplifies to 1/2 dH. Looking at the illustration in figure 1-5, integral h dB is defined as the area between the characteristic and the vertical axis. If we start at point A on the hysteresis loop, and notice that the vertical axis is characterized as volts-seconds and the horizontal axis by current. In other words, we're just thinking of this in electrical terms to make it simple, but realize that underlying volts-seconds is flux density and underlying current is field intensity. As we start at point A, there is no energy whatsoever stored in the core. As we move from A toward B, the area between that characteristic and the vertical axis represents energy. Now, the question is, as we move from A to B, are we putting energy into the device or are we taking it out? Well, it turns out that the convention is this. If we're putting energy in, the sign of the energy is positive. Positive sign on the energy means we're putting energy in. Now, energy is the integration of the integral volts-seconds times the current, or integrating along that vertical axis. As we're moving upward from A toward B, the voltage must be positive. Now, when we're down at A, we're below the horizontal axis. That means the volts-seconds at that point are negative, but the voltage is positive if we're moving upward. The fact that we're negative in volts-seconds at point A is simply as a result of history. We ended up at point A because of what happened before. But at the present moment, if we're moving upward, voltage must be positive. The volts-seconds, even though it's negative at A, is moving in a positive direction. And of course, if we're in the fourth or the first quadrant on the right side of the vertical axis, current is positive. So that from A to B, all the way, the sign of the energy is positive. Positive voltage, positive current. And therefore, the integrated area indicated by the horizontal cross-hatching represents energy we are putting into the core. At point B, that total energy has been put in. Now, we reverse direction. We go from B back towards C. Now, the volts-seconds throughout that entire excursion, the volts-seconds are positive. But the voltage is negative. It has to be negative if we're moving in the negative direction along that axis. And so we're still in the first quadrant. The current is positive, but the voltage is negative. That means the sign of the energy is negative, going from B to C. And therefore, the integrated area indicated by the diagonal cross-hatching, that represents energy being removed from the core and returned to the circuit that's driving this core. So what we're left with is the enclosed energy within the hysteresis loop. By the time we get back to C, there is no more energy stored in the core. It's been returned. Some of it has been returned to the circuit, but most of it has been lost, the area within the hysteresis loop. Now then, just to carry this a little bit further, if we go from C toward D, what is the sign of the energy? Are we putting energy into the core, or are we taking it out? Well, from C to D, the sign of the voltage is still negative because we're moving in the negative direction. And in the second and the third quadrant, the sign of the current is also negative. Therefore, the sign of the energy from C to D, the sign of the energy is positive. We're putting energy back in. And going from D to A, we're taking part of that energy back out. So we have from C to D to A, we have a symmetrical situation compared to A to B to C. So that's what happens to the energy transfer. We put quite a bit in, and we take only some of it out, and the rest is left behind as loss. Now, this core, as we're showing it here, would not make a very good inductor. It does have inductive capability, but what kind of an inductor is it that returns, less than half of the energy that you're putting into it is returned back to the circuit? Most of that energy is going into loss. In order to store significant energy, it's necessary to add a gap in series with this core, and that will linearize the characteristic and skew it out to the right, and we will now get a much increased area between the characteristic and the vertical axis, which represents stored energy. And the amount of that which is gone in the hysteresis loss is proportionately reduced. And so our inductor now is becoming more effective. Now, to quickly run through the transformation of axes as we did before, if we look at the B and H characteristic, the slope on this set of axes is what we call permeability, the ratio between flux density and field intensity. Now, to quickly run through the transformation of the axes as we did before, when the axes are defined by B and H, flux density and field intensity, the slope is permeability, the ratio of B to H. If we now multiply the flux density by the area of a specific core and multiply the field intensity by the magnetic path length of that same core, we now have the axes flux, total flux phi, versus total magnetic force F. And the slope defined on this set of axes is what is called permeance. Permeance equals flux over force. And then permeance, as shown in this slide, is the reciprocal of reluctance. Now, we can think of permeance as being comparable to conductance in the electrical realm, and reluctance is comparable to resistance in the electrical realm. Now, don't make the mistake of equating these. They're not the same thing at all. Resistance is a power dissipating element, whereas reluctance is an energy storage element, really. But reluctance is often a convenient way of describing a magnetic element. We can have a magnetic circuit which is comprised of reluctances that are in series and in parallel. And we can calculate the flux through certain paths using basically Ohm's law and Kirchhoff's law applied to this magnetic circuit. It's not the same thing as an electrical circuit. And there is, however, a relationship between a magnetic circuit and an equivalent electrical circuit. And this is done through a process of duality. And again, that process is described in this paper that we mentioned earlier, deriving the equivalent electrical circuit from the magnetic device physical properties in the back of the Magnetic Design Handbook. Now, to quickly run through the transformation of the axes as we did before, when the axes are defined by B and H, flux density and field intensity, the slope is permeability, the ratio of B to H. If we now multiply the flux density by the area of a specific core and multiply the field intensity by the magnetic path length of that same core, we now have the axes flux, total flux phi, versus total magnetic force F. And the slope defined on this set of axes is what is called permeance. Permeance equals flux over force. And then permeance, as shown in this slide, is the reciprocal of reluctance. Now, we can think of permeance as being comparable to conductance in the electrical realm, and reluctance is comparable to resistance in the electrical realm. Now, here's a little exercise intended to make you feel more comfortable with dealing with this surface which represents energy. Notice that we defined the surface by integral volt seconds on the vertical axis and current on the horizontal axis. And we have 4 different devices that are displayed here. Now, these are not necessarily magnetic devices. They could be, but these are electrical devices displayed on this set of axes. Can you guess what each one of these characteristics represents without referring to the little magnetic design handbook? There are waveforms, by the way, for each of these characteristics that are given in the handbook, which helps to explain them a little more clearly. But just by looking at them, can you tell what they are? Well, let's start with the one on the left. Here we have a perfectly straight line intersecting, going through the origin, and that represents an ideal inductor. Actually, it could be an air core inductor or a gap inductor. It's a straight line, and there's no hysteresis because the characteristic of any non-magnetic material is a straight line. The inductance is not changing. It's constant. The permeability is constant. There's no hysteresis. So that's an ideal inductor which is approached by an inductor with an air gap. What's the next one? Here we have another straight line, but it's oriented at a different angle. It turns out that this device shown here would be a capacitor. Straight line again is as we traverse that characteristic, there's no loss. It's a lossless capacitor. In the characteristic shown in A, the inductor, the relationship between the current and the voltage applied to this device is, of course, 180 degrees out of phase with the comparable waveforms in the capacitor shown in B. All right, now let's go to C. And by the way, these are all driven with sine waves in this case, and it results in this elliptical characteristic shown in point C. What would this device be? Well, it's a resistor, believe it or not. It's a resistor driven by a sine wave will take that shape. Now, it has an open area, doesn't it? That open area represents loss. Every time we go around that ellipse once, the energy represented by the enclosed area is the loss that's being dissipated in that resistor. To show any kind of an element that's going to have loss has to be an open area, a hysteresis loop, if you will. A resistor is nothing but hysteresis. That's all it is, pure hysteresis, if you want to think of it that way. Now, the final characteristic shown in D is an idealized inductor made with a metal alloy core. Metallic materials like molypermalloy and so forth have a near ideal characteristic. Notice that the regions there, the vertical sides of that characteristic, they're nearly vertical. If they were truly vertical, that would indicate an incremental permeability of infinity. And it turns out that some of these metals used for metal alloy tape-wound cores do have very high permeability. Molypermalloy has a relative permeability of maybe 100,000, nearly vertical as seen on a display such as this. Ultimately, that characteristic saturates, and so you see at the top and the bottom some moderate slope. That is the finite slope when the material saturates. What does it look like? If you have a magnetic material which saturates, essentially it becomes like an air core. That characteristic will not go to a horizontal line. That would indicate a permeability of 0, and a permeability of 0 cannot exist. The lowest that permeability can be in the SI system is 4 pi times 10 to the minus 7th. And that might seem like an awfully small number, but it's a number that's responsible. If that, that 4 pi times 10 to the minus 7th ultimately results in inductance of the wiring, inductance of an air core solenoid, and of course the inductance ultimately, when multiplied by the relative permeability, the inductance of any inductor. It all depends on that 4 pi times 10 to the minus 7th value. And that's the smallest the slope will get. Okay, now that does show these metallic materials, even though they tend to be almost ideal, they do have hysteresis. It does take a finite amount of current or magnetic force to change the flux through those devices. Once you reach that critical threshold of magnetic force shown on the current axis at point B, then the flux will change, but it does take time to change the flux, to move up and down in that vertical direction, because we're moving on a volt-second axis. Now, the previous slide gave an example using sinusoidal voltage drive. In this slide, we're using a rectangular voltage waveform rather than a horizontal, rather than a sinusoidal. And we have eliminated the capacitor. Why? Because if you try to drive a capacitor with a rectangular voltage waveform, the current would have to go to infinity during the transitions, which of course is impossible. So we've eliminated the capacitor. The device on the left is our inductor, our ideal inductor. The characteristic drawn out is exactly the same, but the rate at which we move along that characteristic will be different. With rectangular voltage, well, suppose we have a voltage waveform of, let's say 10 volts. 10 volts positive for half a cycle and 10 volts negative for the other half of the cycle. What that will mean is when the 10 volts positive is applied, we will move at a constant rate in the vertical direction. How do I know that? Because that's integral volt-seconds. If the voltage is constant, then as time goes along, we'll be moving at the same rate in the vertical axis. Now, the central figure there, D, that represents our resistor. Look at our resistor characteristic. It's a rectangle, no longer an ellipse, but it is an area. The enclosed area is the loss that takes place in that inductor. But you may not believe that it would form a rectangle like that, but there's no other possibility. Again, consider, so let's say we have a 1 ohm resistor, and we're driving it with a waveform that is 10 volts positive for half cycle and 10 volts negative for the other half cycle. In other words, it's a 20 volt peak-to-peak square wave. Well, let's assume we start at point B, and just take that for granted at the moment. And let's say we start at point B at the very beginning of a positive half cycle. So we have 10 volts now applied to this resistor, a 1 ohm resistor. What's the current going to be through that resistor? Well, throughout that entire positive half cycle, the current must be 10 amperes. So that characteristic must be at the 10 ampere point on the horizontal axis. And all the time, the entire duration of that positive pulse, the current is fixed at 10 amperes. But the movement, it takes place along the vertical axis. If we start at point B, we will gradually move up toward point C. If this square wave happens to be, let's say, 50 kilohertz, that means it's the duration of the positive pulse is 10 microseconds, and the duration of the negative portion of the waveform is 10 microseconds. So we're going to move from B to C, and what is the distance we're traveling along the vertical axis? Remember, the vertical axis is volt-seconds. If we have 10 volts applied for 100 microseconds, then the total distance that we're traversing is 1,000 volt microseconds. So that's the distance between B and C. and it happens to center on the horizontal axis. Now then, at point C, the voltage suddenly reverses. It goes from plus 10 volts to minus 10 volts. And this happens, the voltage changes instantaneously, let's assume. It's an ideal square wave. Then the current will change instantaneously through this resistor from C to F, from plus 10 amperes to minus 10 amperes. That will happen instantaneously. So you see, if you have a characteristic such as this resistor gives us, where we have a horizontal slope, what does that represent? If we think of inductance, that is zero inductance, to have a perfectly flat slope there. And so it is possible then for the current to change instantaneously because no vertical motion is involved in this case. And then, however, it moves instantaneously from C to F. The current becomes minus 10 amperes. It remains at minus 10 for the duration of the entire negative portion of the waveform, and the volt seconds gradually changes from F to G as time passes. We have minus 10 volts, 100 microseconds. Again, that's 1,000 volt microseconds total movement along that axis going from F to G. And then finally, when the voltage then goes instantaneously from minus 10 to plus 10, then the current goes again from minus 10 amperes to plus 10 amperes and changes instantaneously from G to B. Now, that takes care of the resistor. If we look at figure C there, the hysteresis loop for the ideal metallic core is essentially unchanged. And by the way, the little dashed line in there just simply represents a minor hysteresis loop. Now, let's consider the definitions of a transformer and an inductor. A transformer, of course, can step up and step down voltage. It provides isolation. It can provide multiple outputs. But the main thing about a transformer, in the ideal sense, is it transfers energy from input to output. It transfers this energy virtually instantaneously, and storage is undesired. The storage we do get in a transformer is magnetizing inductance and leakage inductance, and both of these are generally undesired. On the other hand, an inductor, its purpose is to store energy. In order to do this and do it effectively, it requires a gap in series with the magnetic material that comprises the core. The gap is where the energy is stored. Now, a filter inductor is obviously an inductor, but a flyback transformer, even though it's loosely called a transformer, is really an inductor with multiple windings. And it does have transformer-like properties. You can have different turns ratios and step voltages up and down, and you can achieve isolation. But unlike a true transformer, the flyback transformer is fundamentally an energy storage device, and it really falls under the class of inductors. And then let's think about our core materials, the limitations of the core materials. And this, to some degree, depends upon whether the windings on the core are driven from voltage sources, stiff voltage sources, or driven by currents. Now, in a switch mode power supply application, a true transformer is normally driven by voltages. Voltages applied in the positive direction and then the negative direction and so forth. Whereas an inductor, from a DC point of view, is usually current driven. If it were not, it would very easily just drift off into saturation. The limitation of the core material is that it will ultimately saturate, and it gives us losses, core losses, which depend on the flux swing. And there is a current component called the magnetizing current, which is non-ideal, and this is a result of the finite inductance of that material. And so in a true transformer, on the primary side, you'll see a current which reflects the load, the secondary current reflected into the primary, plus a hopefully very small additional current in order to drive the core That's called the magnetizing current. Now, as we close this section of the topic, some key points that are worth remembering is that the magnetic force is arranged as a series of equipotential surfaces, and these surfaces are not endless. They're not complete closed surfaces like a soap bubble, but these are surfaces that are bounded and limited by the current which is producing the field. So these surfaces terminate on current flow. Wherever you have current, you will be generating these equipotential surfaces. Wherever you have a surface, there must be current somewhere that is terminating in that surface. On the other hand, flux lines are considered conceptually as lines. They are complete loops. They don't begin, they don't end, and those flux lines are normal to the equipotential surfaces. To change the flux requires time. And this is part of the aspect of energy that's involved here. Time is involved with energy, and time is specifically involved with changing flux. And this becomes more apparent with Faraday's law, which shows that the flux depends on the integral volt-seconds. The energy change is the integrated area between the device characteristic and the vertical axis on this plot of B and H, or volt-seconds versus current. We integrate along the vertical axis because that's the axis where time is involved. And so it's the resulting integral is the area between the characteristic and the vertical axis. And on the energy plane, as we move upwards, and if we're over on the right-hand side in quadrant 1 or quadrant 4, this means we're putting energy into the field. And then likewise, when we go to the other side of the vertical axis in quadrants 2 or 3, downward movement is indicative of putting energy into the field. And then finally, the purpose of an inductor is to store energy and to release it, of course, when we want it back. However, the purpose of a transformer is to instantly transfer energy without any energy storage, hopefully.